In this tutorial we will be looking at L-section matching and how to implement it in microwave office. First of all, let us recap on how L-section matching works. We will be looking at the same example from the book, where we have a simple resistive circuit with an internal impedance equal to Rs and a load which is purely resistive equals to RL. In this case, RL is much greater than Rs, and this is the typical case when L-section matching is particularly useful. We want the load resistor ideally to look just the same as the source impedance. So the first step towards this is to put a capacitor in parallel with it, because this way we will have additional current drawn from the signal generator, which will be used to charge up the capacitor, and hence the overall current which flows through the parallel of the capacitor and the resistor will increase. However, the amplitude of the voltage that we have across the parallel will be the same as the one that we had across the resistor. Because of this, the ratio of voltage and current will be decreased. We have the same voltage but higher current, since we have an additional element drawing additional current. And hence the magnitude of the impedance seen by the generator will be lower. However, what we have done is introduce a reactive part in our load, and this is due to the capacitor. This reactance will be negative, and hence to compensate for it, we'll need to use an element which has got a positive reactance, and that is of course an inductor. This way the reactive elements cancel each other out at the frequency of interest, and if we've chosen a value of the capacitor which has allowed us to make the resistive part of the load look like the source impedance, then we will have maximum power transfer. Now I would like to revisit how we worked out the impedance at a specific point in a circuit in the past, and show you a different way to do it, which would be advantageous when it comes to L-section matching. So let's go to Circuit Schematics, open a new schematic. We'll call it L-section. Now let's go to Project Options and set the frequency of operation to the frequency we're interested in. In this case we'll be working at 100 MHz, so I'm going to change the entry units to megahertz, type 100, select single point and then apply. And then as usual we'll go to the Global Units tab and we'll choose units which will be advantageous for us in this circuit. We'll leave the inductance to nanohenries and change the capacitance to picofarads. Now let's start putting some elements in our schematic. First of all, a signal generator and its internal resistance. So we press Ctrl L and source the elements. I have chosen a magnitude of 2 volts for a signal source. This will just make these numbers more intuitive, but you could have chosen anything. Now let's set the internal impedance of the generator to 100 ohms, which is what we had in our example. And also let's change its name to RS, just to make it more recognizable. This point here is the point of interest to us, because this is the point where the voltage and current will determine what impedance the generator sees. So what we're going to do is insert a voltage and a current meter so that we can then work out what impedance is seen at that particular point. So now we have a voltmeter and an ammeter which allow us to work out voltages and current at a specific point in the circuit, and then by manipulating them we can see what impedance we are actually seeing. Before starting with L-section matching, let's see how we can work out the impedance at this point. We'll first see the method that we used before in other videos, and then I'll show you a different one. So let's use a capacitor as a load to begin with. Let's give it a value of 5 picofarads. So now let's go to graphs, select a new graph, call it voltage and current. The type has got to be rectangular. Click on create, and then, as we did before, we'll add a couple of measurements. From the nonlinear section, we'll choose voltage and then V time. To see the waveform across the load, we will select the measurement element V meter, and then click on apply. We'll do the same for the current, so we'll select I time to see the time domain waveform, and we can choose either elements for the current because the current is the same across the whole circuit, but let's choose I meter and click on apply and OK. The other thing that we can do, because voltage and current have got different units, is associate one measurement with the left axis, with the left vertical axis, and one element with the right vertical axis. So let's right click, select properties, go on to measurements. You can see the voltage is associated with the left, and we'll just associate the current with the right, and click apply and then OK, and then simulate. Now you can see, of course, as we've seen before, that there is a phase difference between the current and the voltage waveform, and what we did earlier was to put a couple of markers on our waveform, one for the current and another one for the voltage, and then we looked at the peaks for both, and we looked at the ratio of the amplitude of the voltage and amplitude of the current to work out the magnitude of the impedance, and then we looked at the difference between the timestamps for either peaks or zero crossings to work out the phase difference between the two waveforms by using a formula that included the frequency. This is all well and good. However, of course, means that you have to fiddle with the graphs and the markers and do your calculations. Is there a way that allows us to actually get the impedance calculated by the simulator and displayed on a graph? And the answer is yes, there most certainly is. Now, the first thing that I want to do is show you how you can see a vector representation of the voltage and current. So effectively, you know what frequency you're working at. You are kind of in a sinusoidal steady state, as we've seen in the book. And hence, knowing that the frequency of everything in the circuit is the same, you can just look at each quantity as vectors with a magnitude and an angle. And this information is sufficient for you to calculate impedances and any quantity in the circuit with the knowledge that the frequency is fixed to a specific value. Now, how do we do this in Vphase-Iphase? Well, let's go to graphs and then select new graph. In this case, we'll go for a polar plot and we'll call it voltage phasor. Now, right click on the graph, go to add a new measurement, and we'll go again onto the nonlinear section, select voltage, and then vcomp. This measurement allows you to see the amplitude of your sinusoid and its phase. So this measurement gives you a complex number which for a sinusoid represents the amplitude and the phase. You may be wondering what this business of harmonic index is. Now, in a circuit, usually you have a fundamental frequency, and then due to nonlinearities or other problems, you have also harmonic components of that frequency, which are integer multiples of that frequency. And the simulator allows you to see signals of frequencies which are multiples of your fundamental one, because sometimes this may be really useful. You need to know what's going on. In our case, because we've got ideal elements and stuff like that, we won't really have harmonics as such, and hence all we're interested in is the one frequency, the fundamental. And the fundamental has a harmonic index of 1. You can see that as I change this to 1, we get 100 megahertz as the frequency we're looking at here. So now I'm telling the simulator that I just want to see the amplitude and phase of the voltage at 100 megahertz across the load. Recall that V meter is the measurement component that is across our load capacitor, so this is the one we have to choose. Also make sure that in the complex modifier section you've actually selected complex, because you need amplitude and phase. Now click on apply and then OK. Now simulate. So now we've got a polar plot of our voltage. So this effectively represents a vector, a phasor, which has got an amplitude and an angle that gives you information about the voltage waveform. Now let's insert a marker here, press Ctrl M and then click on this point. You can see it's giving you the readout in terms of real and imaginary part, but what we want to do is change this to have a readout as magnitude and angle. And you can see that now you're being told that the magnitude of the voltage is around 2 volts and the angle is about minus 90 degrees. We can do the same for the current. So let's go to Graphs, New Graph, Polar Plot, and we'll call it Current Phasor. Right click on the graph, add a new measurement, current. We'll choose IComp yet again, so this gives you the information about the magnitude and phase of the current waveform at 100 megahertz. So select the harmonic index to 1 and then pick the right measurement component, which is I meter, although you could have had either. So press apply and then OK and simulate. And we can see that the current has got a phase of 0, whereas the voltage, as we've seen just now, has a phase of minus 90 degrees. Now let's put a marker on here as well, and again change it to amplitude, magnitude and angle. And now what we can do is display these two graphs next to one another. Go on to Window, Tile Vertical, and now you can see how the current leads the voltage in a capacitor. And you can see clearly that there is a 90-degree phase shift between them. The reason why I'm not displaying them on the same graph is that they have different units, as we've seen before. But with a polar plot, I can't actually have two different axes like I had with a rectangular one. So instead I'm setting up two different plots and I'm displaying them side to side. Now let's go back to our schematic, and now we can swap the capacitor for an inductor and see what happens. Right click, choose swap element and then pick an inductor. We'll give it a value of 400 nanohenries and then click on simulate and display our graphs side to side yet again. Now you can see that in this case the voltage leads the current by 90 degrees, which is just what we would expect for an inductor. Finally, let's go back to our schematic and change the element to a resistor. So we go back to the schematic, right click, choose swap element, type resistor in there, and let's say we just type in 50 ohms and click on simulate. Now let's close our schematic again and display the graphs side to side. And you can see that in this case voltage and current are perfectly in phase with one another. So now I've shown you a way to display the voltage and current as vectors in a sinusoidal steady state. But what we'd like to be able to do is, instead of displaying the values in a graph, is to have the values for the magnitude and angle of voltages and currents in a variable, so we can then calculate their ratio. And this can be done quite easily in Microwave Office. We can go to Output Equations, right click, select New Output Equations, call it L section equations. And then we can add an output equation in one of two ways. We can either click on the output equation icon up here, and a window opens up which is just the same as the window you would get for a measurement. So we can just select iComp as we did before for imeter amp 1 and harmonic index of 1. And the only thing that we need to add here is a name for the variable. We'll call it IL. So now basically what will happen is that we will store the value that we displayed on the graph for iComp, which shows the amplitude and the phase of the current, into a variable called IL. This will be a complex number which gives amplitude and phase. So let's click on OK, and then click on the schematic to place the variable. There is another way to add an output equation, which is slightly simpler. You can just click on the graph, which contains the data that you want to store in an output equation, and just drag it onto the output equation canvas, and then click to place it. And now you can see that this variable has been added, equation 1, which contains the value of Vcomp for Vmeter VM1. What you can also do is change the name of the equation in this case, because you haven't set it yourself, it was automatically assigned by Microwave Office. So you just right click, go on to properties, and then change the name of the equation up here. We'll call it VL. You can see that this is Vcomp at harmonic index 1, which is our main frequency, for Vmeter VM1. Click on OK. So now we have voltage and current at a specific point in our circuit. And what we can do is calculate their ratio. Now we can add an equation to do this by clicking on the equation icon up here. And make no mistake, this is not an output equation. This is just a simple calculation that you're doing by using data from the output equations. So we'll call this Z, and we say Z equals to VL divided by IL. So we know that VL is a complex number, IL is also a complex number, and hence Z will also be a complex number. Now we can add a graph of rectangular type. We'll call it impedance in Cartesian form. And then we can right-click on the graph and add a new measurement. What we want to display in this graph is the real and imaginary part of the impedance. So to find this value of Z that we've set in the output equation canvas, we just click on output equations under measurement type, and then choose the equation we're interested in. In this case, it's Z. Now Z is a complex number, so we can display, for example, its real part. Click on Apply. And its imaginary part. Click on Apply. And OK. Then click on Simulate. Now you can see that we've got an imaginary part equal to 0. And that's perfectly sensible because we haven't got any reactive elements. As you may recall from our schematic, the last load that we put on was a resistor. And hence we would expect from the impedance graph an imaginary part equal to 0 and a real part equals to the resistance that we've got on the schematic. Now if we go back to our schematic and change this element with a capacitor by using the swap element option and set its value to 5 picofarads as we did before, and then simulate, we'll see on the impedance graph that we've got a 0 for the real part and a finite value for the imaginary part. And this is again sensible. And this is because we've got a capacitor which is ideal. There is no loss in the capacitor whatsoever. So the real part of the impedance, which accounts for losses, is equal to 0, whereas the imaginary part is some negative value because capacitors have negative reactance. Now let's go back to the schematic yet again and change this element to an inductor. So let's go to swap element and choose inductor. And we'll set it again to the same values we did before, 400 nanohenries. Click on simulate. And then let's go back to our impedance graph. Now you can see that again, the real part is 0 because this accounts for the losses in the case of a reactive element, and our element is ideal, so it has no loss. And then we have an imaginary part, which is some finite value, and is positive, of course, because inductors have got a positive reactance. So now we've set up our schematic, which has got elements in it, which then allow us to display the impedance as a specific point in the circuit. So we're looking at this point here, which is what the generator sees, and we can measure the impedance at this point, no matter what we put on this side here. Now we are in a position to start doing our L-section matching. First of all, we had a source impedance of 100 ohms, so let's just set that to 100 ohms. So to begin with, we had a source resistance of 100 ohms and a load resistance of 1000 ohms, so let's put that in. We can call this RL to make it more recognizable, and add a ground reference. Then connect it to the generator. Now if we simulate and have a look at our impedance graph, we can see that we've got an imaginary part of 0 and a real part of 1000 ohms, which is just what we would expect. Now, as we said, what we want to do is add a capacitor in shunt with the resistor. So let's do just that. That's our first step. And this capacitor basically allows us to have a lower impedance seen by the generator. The way this works is that now we don't just have a resistor as a load for our generator, we've got a resistor and a capacitor. So the overall current drawn by the parallel of the resistor and the capacitor is higher than that was drawn by the resistor alone. However, the voltage across the parallel is the same. So we've got the same voltage but a higher current, and hence the impedance seen at this point will be lower. How much lower? Well, it depends on the value of the capacitor. So what we're going to do here is insert a capacitor, as we've done, of a random value of 1 picofarads, and then we will use the tune tool to tune the capacitor until we get the right value for the real part of our resistance. So let's simulate and go back to our graph here. Now you can see that the real part of the load impedance now is lower than it was before. Let's just put a marker on it, Control M, and then click on here. But also you can see that you've got a reactance as well, which is negative since we've got a capacitor in parallel with the resistor. Let's put a marker on here as well. Now if I open the tuner and select a range for the capacitor which gives me a bit of leeway, say 1 to 10, say 0.5 to 10 picofarads, and then I start increasing the value of the capacitor, you can see how my impedance decreases more and more. So the bigger the capacitor, the more current the parallel will draw, the voltage across it will stay the same, and hence the impedance overall decreases. So I want to have a real part of the impedance, of the load impedance, which is the same as the source resistance, so 100 ohms. So I can just increase the value of my capacitor until I get to about 100 ohms. So we can see that for 4.77 picofarads we get to a value which is really close to our source resistance. So now we've done one bit of the matching, in that we've got a load impedance which has got the same resistive part as the source resistance. But now what we've got here is also a reactive part which we need to get rid of somehow. So what we can do now, seeing that this is a negative reactance, is use an element with positive reactance to basically cancel it out. So let's close the tuner and go back to our schematic. Now we don't need the capacitor to be tunable anymore because we found the right value for it, which gives us the right resistive value for the load impedance. But what we need to do is replace this wire here with an inductor. And if we choose the value of the inductor appropriately, then at the frequency of interest, the two reactances, that of the capacitor and the inductor, will cancel out. So let's start with 400 nanohenries, but make this value tunable. Now let's simulate, and let's go back to our graph for the impedance. You can see that the imaginary part, the reactance of the load, has already decreased considerably. We've gone from minus 300 to about minus 45. Now let's open the tuner yet again and tune the value of the inductor until we get an imaginary part for the impedance equal to 0. And we can see how for 478 nanohenries you basically get to a point where you're close enough to cancelling out the reactive part of the load impedance, which was created by the capacitor. So if we go back to our schematic now, you can see that we have the elements with the right values, which will allow us to have maximum power transfer between the source and the load.